I'm going to kick things off. Hello, everyone. Welcome to the International Space Elevator Consortium's webinar. We are going to be presenting to you a webinar by John Knapman. It is entitled Multi-Stage Space Elevator Research and Development. In addition, if you don't already receive the ISEC newsletter, please do so. Go to isec.org. You can sign up for the newsletter. You scroll to the bottom and there is a sign up place down there. The ISEC yearly membership, very, very affordable. Students are $25 US, professional is 50, and a family is 95. So please consider joining ISEC. We're a volunteer organization. We are a nonprofit, and we're here to help promote the space elevator. Our next webinar you can find on our events page by going to isec.org events. All right. Hello, welcome everyone to the webinar, Multi-Stage Space Elevator Research and Development, presented by John Knapman, Director of Research with ISEC. John Knapman has worked in astronautics since 2004 and space elevators since 2010. He is Director of Research for the International Space Elevator Consortium. He has a degree in mathematics at the University of Cambridge, UK, and a PhD in artificial intelligence at the University of Edinburgh, UK. For many years, he worked at IBM in roles ranging from sales support and research and development. And with that, I am going to turn things over to John. I'm going to stop sharing my screen. And John, when you're ready, please begin the presentation.
I will. And now I've clicked the button. And then I have to press the share button.
That's correct.
And then I will go to full screen. So you should be able to see I've clicked it now.
You need to do from slideshow from beginning.
Yeah, slideshow from beginning. Let's try that again. Right, now we have the full screen. You should be able to see that.
Yes, we do.
Right, hello everybody. As Karen has said, that's what I'm talking about. There are still some research questions here, because the work does address some areas that have never been addressed before. So some of the material I'm going to cover will be familiar to a few of you. There is some new stuff as well, but I need to go over the introductory part for the sake of those who are less familiar with it. So I'm going to talk on 5 topics. First of all, I want to explain how this work is one of 2 parallel tracks, which I think will eventually converge. Now, then I want to introduce the concept of dynamically supported structures. Then I want to explain how climbers will ascend the multi-stage space elevator. Then I'll talk about development activities that are currently underway, and then some thoughts about the way ahead as I see it. And I will ask your opinion. This is not a quiz, this is your opinion at 3 or 4 points when we get to the end of one particular topic, just so we can have some interaction and some feedback. So the 2 parallel tracks I'm talking about are light, long and strong materials. We're actively pursuing work on single crystal graphene, which is an excellent material with the right properties. And Adrian Nixon is leading a team that he's assembled. There are other candidate materials as well, boron nitride and carbon nanotubes. But the graphene is our best bet. It looks like the favorite. But another option that complements that approach and is going in parallel with it is to use materials that are less strong. And the multi-stage space elevator is one of those, and there's a prototype under construction. The idea of trying to see how we can build a space elevator with weaker materials, to the best of my knowledge, goes back to Ben Shelef, who worked out what was the minimum size of space elevator tether that you need in order to be able to work, but without having to spend all your time just maintaining and repairing it. And that led to something called the feasibility condition, which in the end came down to working out that if the mass of the tether gets much beyond 6,500 tons, then it's too much and you'll spend too much of your time just maintaining it. So that thought does underlie some of this work. Now I'm going to talk about graphene. Can you see the top of that screen? Because top of that, Karen, can you?
Yeah, we see the carbon family dimensions.
All right, because I've got a row of options there, but so long as you can see it, that's fine. This is one of Adrian Nixon's charts, but I wanted to show it to get the balance and illustrate the two parallel topics. On the left, you see 3D materials made of carbon, graphite, diamond, of course, everybody's favorite, soot, and carbon black. And the top right, you see graphene, the material we're most interested in, a 2D material, which means that it is just one atom thick. That is 1/3 of a nanometer thick. It's made entirely of carbon bonds together with very strong bonds, and it yields a very high strength, and in small quantities it's been made at extraordinarily high strength. Carbon nanotubes have been around for longer. They're an example of 1D material because you can only extend them in one direction, whereas graphene can be extended in two directions. You can also put multiple layers of graphene together, but they still retain the properties of graphene. And there's also fullerenes, which can't be extended in any direction, but they are an interesting object. So Adrian proposes the principle for making continuous single crystal graphene sheets using a substrate, using liquid metal instead of the existing method, which is doing it on copper film. If you use liquid metal, then it should be easier, much easier, to pull the completed graphene off the surface of the metal without doing it any damage. And that technique's been pioneered in South Korea with boron nitride. So that looks very, very hopeful, and we're very excited about that work. So light, long, strong materials, single crystal graphene with a tensile strength of 130 gigapascal, density of 2.3 times water. So we need the specific strength because it's got to be light and strong. So if you divide the strength by the density, the mass density, then you get that number 56, which is in megajury, which is a unit we've invented for space elevators because the other units don't apply very well to space elevators. So the biggest piece that's been made so far is 50 centimeters square, 20 inches square, but it's very, very promising. Single crystal hexagonal boron nitride is not quite so strong, but it's still good. It's better than we need, gets to 45 megajury. The minimum strength we need, as I mentioned, calculated by Ben Shelef, is 38 megajury in what I call the standard model. That is the model that we usually talk about for the space elevator. The best available now is commercially is carbon fiber yarn, which comes in as about 1/10 of what we need. It is possible to use that with a multi-stage space elevator, although as I'll explain, I prefer something in between. So here's an illustration then. There's the standard model at the top. The tether is anchored to the Earth at the equator. It rotates with the Earth, and at the other end, 100,000 kilometers away, is the apex anchor. So the upper part of the tether, the furthest away part, acts as a counterweight to the part that's nearer the Earth. The multi-stage space elevator has between 2 and 5 stages rather than just one. And those stages are supported using a technology that I'll talk about. They are supported from the Earth upwards rather than hanging from orbit downwards. And that can use weaker materials right down to 3.9, as I said, commercially available. Anything over 11 will work with just 2 stages. 2 stages is the minimum. In theory, I suppose you could have 1 stage, but 2 stages will work very well with 11 megajury. And if you've got something like 15, it'll work better still. So there's a bit of more detail of the 2-stage version, enlarged, but still the same Earth. The first stage, 100 kilometers above the Earth's surface or away from the Earth's surface. The second stage, 6,000 kilometers. And I'll talk about that for the rest of the time, rather than going into detail about the others. So the multi-stage space elevator reduces the strength requirement for the tether, and it's even possible to use commercial carbon fiber. It's because it supports the part of the tether nearest the Earth where gravity is strongest. And there's a lot of detail about it in the 2018 ISEC report, which is at that website. You can access it online free of charge, or you can buy it, a printed copy, through Amazon. So that brings us to the first question. So I like a bit of interaction, and since we can't be in the same room together, we can do it this way. Question 1, we'll use Karen's technique. What do you think is the most likely material actually to be used in the first space elevator? You can see the options: carbon fiber, carbon nanotubes, single crystal hexagonal boron nitride, single crystal graphene, or something else. Okay, Karen?
Yes, I was just saying, I have a poll. We're going to do the annotation when there's a little more complication to your question, which is great. But here we are. So just to go ahead and select which you think it is. We're going to let everybody make their choices here. We're still waiting for everybody. I know we have a handful of people here and some people here who are, we've got 21 of you out of 28. So a few people need to vote. Okay. All right. I think most people have voted. I'll just give you a couple more seconds, and then I'm going to end the poll and show the results. Does everyone see the results there?
Yep.
So we have 2 with carbon fiber and another material has, let's see here, make sure everybody sees that. There we go. Share results. Here we go. So we're sharing them out. So carbon fiber, 8% of you. Carbon nanotubes, single crystal hexon boron nitride, that's a mouthful. And then, of course, single crystal graphene has been the winner.
Great.
All right, so I'll go ahead and hide the poll, and we'll go back.
Right, I still see the poll at the moment. Are you going to hide it?
You need to click on it. I did hide it.
Okay, I clicked on it. Okay, fine. All right, let's move on then. Oh yeah, fine. So now we're on to topic 2. What is a dynamically supported structure? So here's an illustration which appears on the cover of that report I mentioned. You see here the first stage at 100 kilometers above the Earth's surface, the Earth port down at the bottom. In between, there are evacuated tubes which carry fast-moving objects, magnetic objects. I call them bolts by analogy with the bolt of a crossbow. And they reach the first stage where they are turned round using magnetic levitation, and they go back to the Earth port where they are turned round again, given a speed boost to make up for any losses due to friction, and continue in a cycle. And some more of them go on higher. But that's the basic principle. This is an example of a dynamically supported structure, an idea that was first proposed, to the best of my knowledge, by Keith Lostrom quite a while ago for launching spacecraft. His idea was a much longer launch runway, really, 2,000 kilometers long. So electromagnetic propulsion for spacecraft would accelerate them over that distance to orbital velocity, 8 kilometers per second. That's 80 kilometers high, so just high enough to be above most of the atmosphere. And that, again, held up by objects traveling inside tubes. You see those tubes going down to the left there. At the bottom is a structure, a horseshoe-shaped structure that turns them round. Keith calls them turnarounds. I call it an ambit. and in the same way, objects go round and round, and you use some of their momentum to accelerate the spacecraft. So that's the concept of a dynamically supported structure. And applying it to the space elevator means, first of all, looking at the Earth port here, we see the tubes, the evacuated tubes in white, going up to space. Next to that, you see a couple of orange cables. I propose winching from the first stage, although there are other ways of doing it. It would be possible to climb the tubes or have a tether that you climb. That's an option as well. But I'm not trying to show, I don't want to show too many options. I just want to get through the concepts. There is a method for stabilizing those tubes, which means that they only need guy wires for the bottom couple of kilometers. So guy wires are illustrated there. I'll talk about the stabilization next. But also on that picture, we have superconducting magnets, which are necessary because the bolts will be arriving at high speed down those tubes, and they need to be turned round sufficiently to stop them hitting the ocean bottom. And so we need superconducting magnets for that, and they will go round, they will go past those thrusters, which will give them a speed boost, and then back up and so on. So that's the setup of the Earth port. Now, the active curvature control algorithm is the method for stabilizing in wind. And the idea is that instead of having guy wires all the way up, you only need them at the bottom because you adjust the curvature in order to force the bolts to go round a bend, and that creates a centrifugal force which counteracts the wind. And that has the effect of transmitting that wind force down to the guy wires, where they can be used to pull the tubes back to the vertical by the time they reach the lower ambit. This technique has been proven mathematically and demonstrated in simulation, and I hope that I will see it demonstrated in practice before too long, but there is still a road to travel there, but we have people who are working on it. So this is what the first stage looks like. Here's the first stage. You see the other end of those evacuated tubes. I mentioned cables, which are pulled up by winches. You see those yellow semicircular structures, those are ambits. And the bolts that arrive through the tubes enter the ambits, where magnetic levitation turns them around and sends them back down again. As you know, Newton's second law, force equals rate of change of momentum, means that in pushing them down, that creates an upward force. And it's possible to set that up so that you get actually several hundred tons of force if you need it to support quite a substantial structure at that point, as well as hold up the weight of the tubes and any climbers that need to be pulled. Then above there you see the tether, the white line in the middle, which goes on up a long way up to all the way through geo to the apex anchor. And then you see those orange lines, they're brown lines actually, they represent the streams of bolts, because in space we do not need evacuated tubes. And in fact, when dealing with space debris, it's better not to have tubes, because tubes could be damaged by collisions with debris, whereas the bolts, if a couple of bolts are lost, they're expendable. The others will carry on. So that's the principle of how the bottom, the surface and the first stage work. Now, the idea of an ambit is something that I need to explain a bit more about how it works. I've only got a simulation at the moment. We don't have a working ambit yet, but it enables me to explain how we work with high temperature superconductors, which we have been doing. The ideal temperature is 50 degrees K, but the actual temperature so far has been just 86 K, which is cold enough to get superconduction, but only just. The feature of high temperature superconductors is that they have two they create two magnetic fields. So we've got that bolt there, which is made of permanent magnets, and it's traveling in between two tracks made of high temperature superconductors. Now the blue object is the mirror of the bolt, and there's another one on the other side, and that provides stability. It follows the bolt. Effectively, it's behaving like a diamagnetic. It follows the bolt. I'll show you the simulation in a moment, and keeps it stable. Now, the second feature of high temperature superconductors is the trapped field, which is frozen in while the HTS is being cooled, and the trapped field provides levitation. This is unique to type 2 superconductors, high temperature superconductors. So what you have to do is set up permanent magnets or possibly coils inside the track all the way around, then drop the temperature. And so you insert your coolant, which in our case is liquid nitrogen, but will be something else later. And that then, as it reaches superconducting temperature, the field becomes trapped in the superconductor, and that provides a levitation force. So you've got two fields now. You've got the mirror field, which is making it stable, and you've got the trapped field, which is frozen in and is providing the levitation. So in the simulation, you see there, you can see how the mirror field moves with the bolt, but the levitation is needed because we're going round a bend as the ambit does, and make sure that the bolt does not fall out, does not fly out, but emerges from the other end as required. And the HTS we're using is YBCO. There are others, but that happens to be the most suitable for this application. So that's how the ambit works. And in those high temperature superconductors, we need to attach cooling blocks. So we use copper blocks for cooling, and the plan is to use electrolysis to attach a thin layer of copper to the high temperature superconductor, and then solder the blocks onto that. This is a method developed at the University of Cambridge, which who've been very helpful in giving us some advice on how to achieve this. The engineering department there. So that's how the ambits work. And so then there's another ambit at the second stage at 6,000 kilometers from Earth. And that is where the streams of bolts arrive in order to go through the ambit. They left the Earth at about 7.7 kilometers per second, and they arrive here at about 1.8 kilometers per second. And they go around, and in the same way, they create an upward force. Now, you'll see the tether going straight through, but it's important to realize that those blocks there act as a gate, and they support the tether below. And there are, in fact, another pair of gates at the underneath side of this second stage, and we must only ever open one gate at a time in order to hold up the weight of the tether below, because the tether above cannot support the weight of the tether below. So that's how the first and second stages work. So now I want to have another poll and see what you think. Do you think dynamically supported structures have a future? And there are various suggestions about where, and of course there's a possibility of no. I don't think we're allowed for no here. We're a very positive organization. Would you like to vote? If you think no, then just don't answer.
You can type no in chat.
Okay, yes, you can type no in text. Okay, fine.
So we have a little more than half, and it does seem like we have a winner.
Well, I think it is allowed.
Ah.
Are they allowed to vote for more than one, Karen?
Actually, no, I did not set it up for them to vote for all of them. Sorry about that.
Didn't think of
but
that.
type in the chat if you do think it's all.
Yeah.
That would be interesting to see.
Yes, I didn't think of that, nor did you.
No, neither did I. So we have one who wants all of choices. That would be Dennis. So that's great.
Fine.
All right. All, definitely. Obviously, we should have included that. Oh.
Yeah, that's lacking in foresight there, Karen, I think.
That's very true. We should have thought of that. All seems possible. Well, that's great. All right. So I'm going to go ahead and end the polling and share out our results. So there are a number of people who did say all, but the majority here are for space elevators.
Good.
So did you want to speak anything more to that? I mean, there's other applications and launching spacecraft, civil engineering. So they all probably are good choices. So I'm going to go ahead and hide that poll. So you do the same, John, just click the X and then we'll move back to the presentation.
That's fine. Good. So now I want to talk about how to climb the multi-stage space elevator. So here is the first stage. I suggested winching, as I said. It is possible to use a mechanism of climbing up a tether dropped from the first stage down to the Earth. That's another possibility. In this method, the climber is that red box hanging on that cable. We winch it up, and then it emerges, and we move it over to the tether and engage with the tether. This would be an automated process. It would most likely be operated by remote control from the surface, from the Earth port, rather than completely automated, but it wouldn't generally involve human beings working there. They would only be needed to go and fix problems. And then the tether goes on, then the climber goes on up the tether. So that's how, oh yes, and I wanted to say there is the option of having 3 tethers instead of 1, which has some advantages, and that they could go all the way up to the second stage, or they could join the main tether higher up. This has some advantages when you think about space debris, because there's just the faintest possibility that even with 2 tethers, if you're really unlucky, a piece of debris could go straight through both of them. But it's not possible for a single piece of debris to go through all 3. And that's the thinking behind 3 tethers. It's an option which will work with this setup. If you want to make them further apart, you just need to add some extra struts on the side. You could even have 4 tethers. So I wanted to mention that option. And then when we get to the second stage, the climber passes through. So there it is. It's nearly reached the second stage, and then it's just underneath. So the gates now open at the underside. Then the climber is now inside the second stage, and the gates close underneath it. Then we open the gates above, and the climber comes through. So that at no time is the tether left unsupported. Now this just shows the same climber going through, but we may well decide that we would like to make some alterations to the climber mechanism at that point. We could say, since the climber is much lighter, above 6,000 kilometers, it could go a lot faster, and we don't necessarily need to carry the extra equipment all the way. We could keep some spare equipment on the second stage and change equipment in order to go for a higher speed. That's a possibility. That's an option, something we can bear in mind. And I'll come back to that a bit later. Now, another factor that's important is the climber experiences a Coriolis force as it ascends. And that's illustrated here. As you know, the Earth rotates, and that's its rotational speed at the surface, at the equator. And as climbers ascend, because the tether stays at more or less the same place above the same place on Earth in a straight line, constant angular velocity means that the linear velocity, rotational velocity, increases as it goes up. And so whereas low down, you're traveling at near 465 meters per second, by the time you get to geosynchronous altitude, at about 36,000 kilometers, you're going over 3 kilometers per second, 3 kilometers per second. And in between, you've got all these different speeds. That leads to a slight lag in the tether. Back in 1975, Jerome Pearson published his seminal paper, and part of the title was A Launcher Using Earth's Rotational Energy, because the Earth is providing the rotational energy. You can see that it's transmitted through the tether by a slight lag in the tether. It's just a little bit off vertical, a little bit off the straight line, because the tension in the tether is transmitted to the Earth, and that pulls the climbers faster and faster. And when you get right to the end at the apex anchor, they're going over 7 kilometers per second, which is a fantastic speed. It's enough to travel to other planets at height in quite a short time. Now, with the multi-stage, with 2 stages, in fact, you have to arrange it a bit differently, because essentially we're pushing the lower stage rather than pulling. And so the angle is the other way for that first part. And in fact, we need some control over that angle, depending on what the climbers are doing, where they are, and whether they're going at full speed or not. So you see there, the first stage is running at just a little bit faster than the Earth's rotation. Yeah, even at 100 kilometers, there's a difference, actually, a noticeable difference, and gravity is slightly lower. By the time you get to the second stage, it's going at nearly twice the speed, 902 meters per second to be precise. And so that does need to be taken into account when planning and building. The method by which the bolts travel does enable small movements to be facilitated. I'll explain a bit more about how we keep the bolts going in the right direction a bit later on. So in summary, the Coriolis force, as bolts accelerate, in the orbital direction, as they climb, as bolts climb, they accelerate in the orbital direction, even though the bolts are slowing down as they go away from Earth. So in addition to the climbers, the bolts are also subject to this same Coriolis force. We have to consider both the climbers and the bolts now. So the bolts are accelerating in the orbital direction as they slow down, going further away from the Earth. And the descending bolts do the opposite. As they go towards the Earth, they get faster, but they slow in the orbital direction. So it's possible for them to exchange lateral momentum because they're magnetically connected and electronically controlled. Each bolt contains a microprocessor and some other facilities. There is more detail on this in the report that I mentioned, but there's a mathematical proof as to the stability that you get with this method, and I have done simulations on that as well. It's non-trivial, but it does hold water. Here's a detail of those streams that I mentioned then. But if you want a picture of an individual bolt used for in space, then you do need to look at the report. But the streams are close enough together that they can interact magnetically, and the bolts emerging from one stage help to guide the arriving bolts coming in, so that they enter the right spot. You'll never aim bolts exactly 6,000 kilometers away, but because they interact with each other, they can assist each other to make sure that they arrive at the right spot within a few centimeters, which is enough. So it's time to have question 3 now. I want your opinion about this question of the climber mechanism. Should we change the climber mechanism, or should we have the same climber mechanism throughout? So I've given you some options there, winching and changing and so on. I know I explained in my talk why. What do you think?
So we have people coming in with answers. It's probably neck and neck at this point. So
that's quite interesting, because I can't decide myself. I'd vote both ways if I had to.
So as people are deciding, I'm going to give you just a couple seconds more, and then we'll reveal our results. Looks like people are changing their minds. Okay. All right. I'm going to go ahead and end the polling and share out our results. So there you go. We have 7 same throughout, 6 winch to first stage, then climbed the tether, and then 9, the winner, I guess, change mechanism at first and second stage.
Yeah, interesting.
So kind of all over, kind of broken out between the 3 choices. And of course, one person did say other. So it'd be interesting to for that person who did respond other, can you type in chat and let us know what your thoughts are here? I'm going to
that would be good.
Stop sharing the results here.
Okay.
And go ahead and close that, and we can go back, and we're trying to see if that person will respond to other.
If not, I'll just carry on.
Why don't you just go? It was Grant says it was him. So Grant, if you'd like, you can unmute yourself and maybe share your ideas or type them in chat, or not. It's up to you. Well, perhaps some other time. So John, let's continue with the
I'll
topic.
move on then. I'll tell you about some of our development activities now. So this is the prototype that we are aiming to build first. This is indoors. So it consists of 2 ambits as a basic requirement and thrusters in between. Thrusters just, well, I mean, the whole thing is going to be about 5 meters high. So the thrusters are less than a meter long, a row of thrusters to provide enough, and to test the thruster technology as well. And the intention is this will all be done with high temperature superconductors. That's what we've been experimenting with and working on. So here's the workshop, that our new workshop, which is in the tropics. If you really want to know where it is, ask me afterwards. But it's in the tropics, which is why it only needs 3 walls. And that's where we intend to build this. Here is the thruster coil that's been built, and we're testing it. That's obviously essential to the function. There are still some technical matters to be sorted out here. I won't pretend it's straightforward. The sensors that we need, the position sensors, we're having some trouble with, and we're still working on that. So as a matter of fact, we are just about to start looking for a couple more people to help work on it. So if anybody's interested in that, you can send me an email to research@isec.org, research@isec.org. Although this is not primarily a recruiting drive, we only decided 2 days ago that that's what we wanted to do. And that, of course, when I say we, I mean the people who are paying for this. Here's some recent electronic controls. I earlier, once upon a time, showed some stuff I built myself. This looks much more professional. You can get machines to make printed circuits and place the components on them, which is how most of this was made. And it's much more reliable, and it works a lot better than handmade stuff. At least handmade stuff made by me, anyway. It works a lot better. Many of you have seen this vacuum chamber before, the test rig in the vacuum chamber that we were using a little while ago. Here are the liquid nitrogen connections. And as I said, with this setup, we managed to get down to 86 degrees K, and we really need to get at least down to 77, which is the temperature at which, well, the lowest you can go with liquid nitrogen is 63, but that's at low pressure. So that's the area we're working in, and at some stage we will switch to something else, which will get us down to 50. But this is suitable for what we're doing at the moment. So I mentioned the ISEC report. There's a whole lot of detail that although I could talk about, I didn't think it was a very good idea because it would overburden you with too much. the physics, how we deal with space debris, stability in space, how to maintain it, and the maths and so on, how we deal with friction and minimize it, how the maglev works, linear propulsion, how that works, reliability, how we maintain it, and how we achieve it, how we deal with the very high speed of the bolts, minimizing power consumption, maintenance, construction, and erection finally. So that's all available for you to look at as the reference again at the top of the screen. So finally, I intend to just give you my thoughts about the way ahead. And I'll ask you a question about this at the end as well. So I'm now showing convergent tracks rather than parallel tracks, but they start off parallel and then I think they converge. I probably could have drawn it cleverer, but never mind. So we have the work on light, long, strong materials, and single crystal graphene is our favorite, and Adrian is our champion, but there are other people working in this area as well. Of course, it's an area with a lot of interest and focus around the world. And the multi-stage space elevator, supporting the Tether's weight near Earth. This is a more complex solution, though. What the big disadvantage of multi-stage compared with the standard model is that there's greater complexity. Therefore, there's more scope for things to go wrong. And I can't help that. That's a simple fact. The team and the investors I mentioned are interested in dynamically supported structures more generally, not just for its space elevator application, but for other applications too. And so, even if we get the brilliant material we want and we don't need multi-stage, there are other applications for this technology, so that isn't really a problem for my team. And in any case, even if we have the strong material, we still have to deal with the atmosphere, and the technique I mentioned for handling winds is likely still to be pretty important. So that's my view, and I've got an illustration here. So I mentioned at the beginning, given a tether mass of about 6,500 tons, what can you do? Because we think that's about as much tether mass as we can cope with in order to maintain it and use it successfully. So if you think of a tether reaching down from geosynchronous with more on the side away from Earth in order to counterweight, and you do it with carbon fiber that's available today, it can reach to about 14,600 kilometers, something like that, away from the Earth. If you take it any closer, then it becomes too heavy because gravity increases as you get closer, and the material can no longer support its own weight. I've aimed for the two-stage space elevator at 6,000 kilometers, and at the other end, we have the marvelous single crystal graphene, which is strong enough to do it all by itself, over at 56 megauri. So that's the that's where we are. There's this chasm between what's commercially available and what's theoretically possible and what we hope will be practically possible. So I envisage things gradually coming together as materials develop. We work on the multi-stage space elevator at the moment. It doesn't even reach five meters high, but we're working on that. And as time goes on, I see materials developing and improving, but not suddenly breaking through to seeing everything we need in one go. I see a period of steady progress as things get better and better, but with both multi-stage and with materials development. So you can see they in my dreams, they come together. Now they're almost there. You can just about do multi-stage with 10 megauri, but it's tight. It's not very good. But with 11 megauri, it's great. It's brilliant. And anything better than that, it's even better still. So that's my vision about how I see things going. If it's better than that, so much the better. So then that gives me question 4, after which I just have a summary slide to finish.
And so
we like to see a breakthrough. Go on, Karen.
Yeah, so what we're going to do, we're going to use the annotation tools here. So if you go up to the top of your screen, you'll see something that says view options. So click that and then click annotation. And let's go back to the slide.
Oh, did I change it? Sorry.
There you go. And so click the annotation tool and click whichever tool you'd like, stamp or whatever, because you can place your whatever you'd like. So there's a check mark, and I'll just show you. You place it in there and just check into the box that you think that there's going to be a breakthrough or steady progress. You can use a check mark or a red X so we understand, or even stars or whatever you'd like. And we'll kind of watch as this is going on and see where we all land. You can also type in chat if you have some other comments or other ideas. And a lot of people are starring and check marking. So it does seem like a lot of people think there's going to be steady progress with your dynamically supported structures, and kind of evenly split between the light, long, strong materials.
Yeah, well, there's going to be breakthrough or steady progress. That's fascinating. Is that being recorded, Karen?
Yes, it is. Yes, it is. It is going to be in the recording, and I'm going to grab a screenshot as well.
Good.
It'll be interesting to see how everyone, and if you've recorded your responses, then we'll go on to our summary slide.
Okay. This is a vision of the space elevator. All right, Karen?
Yeah.
So in summary, just to remind you, the space elevator is designed to enable humanity to explore the solar system and even beyond, to enable colonization of the solar system by providing bulk lifting and complementary to rockets. So rockets are faster, but you have to carry such an enormous amount of fuel when you take off with a rocket that bulk lifting using electrical power from fixed infrastructure is always going to be economically more efficient. Even though there are claims for rockets getting better, space elevators will get better too, as we learn more about how to use them effectively. And they will enable us to create new industries, such as space-based solar power. So this is a general point for the space elevator, and the multi-stage is one kind of space elevator, but the benefits are the same. And that's my conclusion. Thank you for your attention.
Thank you so much, John. That was great. And now we have time for Q&A. If you would like, you can unmute and ask your question. As you all know, we are recording, so know that your question will be in the recording as well. If you'd like, you can just type your question in chat. If you have any comments or anything like that, please feel free. We're just kind of have an open time here. You can come on camera if you'd like. I didn't. I'm going to go on camera and say hello, and let us know if you have any questions.
Hi, John.
Hi. Hi, Dennis.
Perhaps it'd be useful if you explained why 2 stages are the minimum.
Well, I did think after I said that I suppose we could get to a point where we might just have 1 stage because of dealing with the Earth's atmosphere. So I said 2 stages was a minimum. It's certainly true that if you've only got 1 stage, then it isn't multi-stage anymore. So there is that logic point. But what I'm envisaging is to take the weight off the tether. You need a second stage. You do need something above the atmosphere because the technology is different in the atmosphere. And then if you only want it for that, then I guess you're right, Dennis, you only really need one stage. I know you didn't say that, but that's the implication of your question.
And there's some questions in chat, John, I'm going to go ahead and ask. So I wonder if when you will be considering the dreaded subject of failure modes.
Well, yes, we have obviously given some thought to that already, but it's true that when it comes to failure, we will certainly discover a lot when we get that first prototype working. But there are some obvious sources of hazards, such as space debris that I already mentioned. In addition, you need to consider power failure, but there is a vast amount of stored energy in this system. You know, it will take several weeks of power to get enough energy to keep the thing going. And so it is possible for it to run under its own momentum for a short while you bring your backup power supply into play. Remember that the power is required at the surface, at the earth port. It's not required above, because you can, if necessary, extract a little bit of power from the bolts as they come shooting past. So the main point is power. If you can think of other failures, like yeah, there is some stuff about possible hazards, I think, in the report, but being hit by aircraft, you know, and that sort of thing, or terrorist action. There's a limit to what you can do about terrorist action, but there's been some thought about that sort of failure mode.
Okay, and then there is another question. Was the decision to go multi-stage based on current limits to tech of tethers?
Current limits to probably mean strength of tethers. I think that's a tech's a unit of strength. Yeah. Yeah, is that a question though?
Yeah, it is. They were wondering if that probably the technology of the tethers, did that have any play into designing a multi-stage space elevator?
Yes. Oh yes, very much so. If we can get hold of a material that meets all our requirements, then it makes the whole construction much simpler. And we still may want something in the Earth's atmosphere for other reasons, like dealing with wind, but we won't need any of the complexity in space. So yes, it has a great bearing. But there are other properties of the tether, such as how slippery or rough it is, which means those gates that hold it up will need to be able to deal with what may be a very, very smooth tether, since the outer layer, you know, just one atom thick. So there are some issues there, but that's an issue for climbers more than it is for the supports in the second stage. So there are questions like that.
That's great. Someone asked the question, any ideas about the actual climbing mechanism on the graphene ? Portion of the tether?
Well, we have done some work on that. There is a study underway, an ISEC study at the moment, that some of us are involved in, which is looking at exactly that question, especially the gripper, the interface between the climber and the tether. Given that graphene is actually is a very smooth material, how do you grip it effectively? And that's something we've been working on.
That's great. And do you have an idea when that study might be completed and published?
Well, I think the timetable, Dennis is the chair of it, but I think the timetable is, we hope to have an interim report by the summer. The final report will be ready probably early next year.
Well, great. So everyone can look forward to reading that study. And as I put further up in the chat, there is a link to the multi-stage elevator report that John did reference, as well as a link to all the reports that are on ISEC's website that are available as free PDF downloads. Right. I do think we have another question. Does the multi-stage design allow for stopping climbers / bolts anywhere within the length of the elevator, or is it the exit / entrance option only available at the anchor points?
not sure if I entirely understand that question. Certainly, climbers may stop if they wish to, and that will affect the balance of Coriolis forces. So that has to be dealt with, and I did mention that. What was that about flashes? I didn't quite understand that point.
I think you can have the let's see, climber bolts stop. The entrance and exit points.
Oh, the bolts.
Of the bolts. Yeah.
Oh, the bolts never stop. They only stop if you shut the whole thing down completely, which means taking it down gradually, step by step. The bolts continue at full speed all the time in continuous motion. It's hugely wasteful to stop and start them. So you only do that at the very beginning and at the very end, or in dire emergency.
All right, but the climbers do have you can pause them and stop them along the
That
length.
is possible, yes, although it's quite complex. I mentioned how the Coriolis force changes and affects the position of the second stage, but it is possible to do that. It needs to be done in a controlled fashion if possible. Well, it does need to be done in a controlled fashion.
Right. Hopefully that answers the question for the person. Any additional questions from anyone? Any additional comments? Okay, I'm not seeing any. Go ahead.
Could I ask a question briefly? Could you explain how you actually build the lower structure in the first place? How you get the first stage to support itself?
Well, I could do. It is in the report. Several pages in the report. So all I'll say is that if effectively you have to raise it step by step. So you need a rather large vacuum chamber on Earth at the construction site, because you need to be able to you have to create a gap between two segments of tube and move them sufficiently far apart to enable another section of tube to be inserted in the gap, and that's all got to be done in vacuum. The bolts are not traveling at full speed at that time, but nevertheless it is quite a complex maneuver. It's something we are hoping as a team that we will actually be able to demonstrate in practice at some point, but not quite as soon as some of us had hoped. I mean, some of us had hoped that it would happen next year, and it's not going to be next year.
Thank you very much. Great presentation, by the way.
Thank you.
There is a question that I know is being discussed in the ISEC.org community. Is the elevator likely to be an alternative to rockets for near-Earth applications? And if so, by when? Do you want to address that question, John?
Yeah, I can talk about that. It's something we've certainly talked about quite a bit. The space elevator is much better at getting to GEO and going to interplanetary destinations. When it comes to low Earth orbit or near Earth orbit, depending what you call it, the Tether is traveling. I showed the speeds at which you're traveling when you're, say, 2,000 kilometers up above the surface, which is typical for near Earth orbit, or even lower. You're not traveling very fast. And in order to get to that position, you really got to go most of the way up to geosynchronous altitude. You've got enough orbital energy, but of course you're in the wrong orbit then. You're going to be in a highly elliptical orbit. So it's not really ideal for near Earth orbit applications, but it is possible to use it.
Sorry about that. Any other questions from anybody? Okay, someone asked a question about space debris. So, all right, so you have a problem with space debris. And
Yes.
as this person understands, you get extra energy out of the system from the Earth. Could debris be used to harvest this energy?
Oh, wow. We think of debris as a problem to be avoided. I'd never thought of trying to get energy from it. One thing we have thought about is trying to use energy from the sun or from radiation, that is certainly possible. And we have considered climbers that are powered by solar power. In fact, that's described in a book that we published in 2013, which I've got, if you can see it, it is this book here. Yes.
As space elevators, an assessment of the technological feasibility and the way forward.
Yes, that's right. That there are 5 editors there, including me. So that is, it does talk about using solar power to power the climbers there. And it's quite an attractive option. The alternative is to transmit laser power from the Earth.
Well, that's a really interesting concept to try and get some energy out of the debris.
There are pros and cons. The solar power shuts off at night, but the laser power shuts off if there are clouds. So, you know, it's an interesting trade-off.
Well, that's really great. We do have a comment from Pete Swan, our president, about checking out 2 reports and 2 IAA reports that cover debris.
Yeah, this is an IAA report, International Academy of Astronautics.
Yes. Any other questions or comments? Could ambits be sufficiently robust structures to allow for space debris capture at several hundreds of kilometers altitude above Earth?
Well, I don't know is the answer to that. That is a very interesting question I hadn't thought of. It is possible. Yeah, it's possible. I mean, the methods that have been proposed are all a bit different, because they usually involve spacecraft in orbit rather than the space elevator, which is not in orbit until you get to geosynchronous altitude. So yeah, I'm not sure, but it's an interesting idea. It's worth working on.
Very nice. Thank you so much. And I would just want to thank John Knapman for giving us that great presentation and really having an informative discussion here. And then I would like to invite you to sign up for our newsletter, where we have a lot of different articles that we publish. isec.org is our website. If you scroll down to the bottom, there is a place to sign up for the newsletter. In addition, we ask you and invite you to become a member of ISEC. We are a volunteer organization, and we have a few little costs here and there. And as you can see, our yearly membership is very, very affordable. We would love you to join. Go to isec.org to learn how. And our next webinar has to be planned, but stay tuned. Go to isec.org/events, and we'll make sure that our next webinar is listed there. And this webinar obviously has been recorded, and we will get this on our website in the next week or so, along with any materials. So thank you so much, everyone, for joining us today. Have a good rest of your day, a good afternoon, a good evening, and a good morning, because we're such a global organization. Thanks so much, everyone.
Bye.